Welcome, friends, to another exciting episode of statistics. So, today, what we are going to do is going to be very exciting because today we are going to solve few statistics challenges. These challenges are based on the learnings which we have acquired over the last few videos. So I assume that you have watched our last few videos, as this video is an extension of those videos. So today we will solve statistics challenges using Central Limit Theorem, using the concepts of normal distribution, and using the concepts of hypothesis testing. So this is Central Limit Theorem, normal distribution, hypothesis testing, and of course central tendency like mean, standard deviation. So let's get started with our challenge. So let's look at the first problem. So the problem says that batsman A scores 50 runs on an average with a standard deviation of 5. So in this case, the scores of batsman A has been compiled, and it has been found that he scores 50 runs on an average and his standard deviation is 5. Now what we want to find out is what is the probability that he will score less than 40 in a given match. So he scores 50 runs on an average with a standard deviation of 5. So if for any given match we have to predict his score, or in this case we want to predict that he will score less than 40, we want to find out what is that particular probability, what are the chances. So let's get down to work. So let's first write down what are the information we have. That's very important for problem solving. So in this case, we know, so this is problem 1. We know that the mean is 50. We know that the standard deviation is 5. So now, since in this problem nothing is mentioned that what kind of distribution does the runs of the batsman is plotted against, let's assume that these 50 runs with a standard deviation of 5 follows a normal distribution. Since nothing is mentioned, let's assume that it is following a normal distribution. So let's draw a normal distribution. So this is 50. So if standard deviation is 5, then one standard deviation to the left is 45. So 2 standard deviation. So what we want to essentially find is the probability of the batsman scoring less than 40. So friends, one thing which I want to tell you is statistics is a subject which mixes numbers with intuitions. So you should not look at just dry numbers. You should always try to visualize the problem and apply a lot of intuitions. This is, by the way, not a very good normal distribution. Let me just... Yeah. So essentially, if you look at the problem is the probability of the batsman scoring less than 40. So what are we trying to find? We are essentially trying to find the region shaded in red. No, I mean, in this case, before you even apply the formulas and crunch numbers, just look at the graph. If you look at the graph, what you will see is that intuitively the chances of the batsman making less than 40 is very less, right? So it's more likely the batsman, if this is a normal distribution, the more likely is that the batsman is going to score mostly in this region, the region shaded in green here, right? Now let's find out what is the probability. So the first step, what we'll do is we'll try to find the z-score of 40. Now z-score, as you know, just a quick recap, z of x is x minus mu divided by sigma, which means 40 minus 50 divided by 5. Though intuitively we can see that it has to be minus 2, but still let's calculate. This is minus 10 by 5 equals minus 2. So now we know the z-score of 40 is minus 2. Now what we are going to do is we are going to look into the z table and find out the p-value. So this is step 2. Step 3 is use the z-score to calculate p-value. So let's come to the z table. Here we can see that the z-score is 2, which means the p-value is 0.0228. So the p-value is now what is p-value? In this case, if you remember our previous videos, p-value is the probability of picking up a random sample from this shaded region, this region, right? Which means the chances of scoring if this is 40, the chances of scoring less than 40 in a given match is 0.0228. If I convert that in terms of probability, I just multiply this number with 100 and we will get 2.22 or 2.23%, right? So this p-value of 0.228, we can say that the chances of the batsman scoring less than 40 is 0.228 multiplied by 100. Just to calculate it in terms of percentage, it's 2.23% up to 2 places of decimal. I hope this problem is clear. Now let's just slightly tweak the problem. Suppose this is not 40, or rather this is 40. This is fine, this is 40. And suppose we want to find this place, say 39. In that case, this part is not what we are looking at. We are looking at only this part. So Z score of 39 is 39 minus 50 divided by 5, which will be minus 11 by 5, which will be minus 2.1. So here if we come, 2.1 is 1.79%. Now if I ask you what is the probability of it scoring, say, greater than 40, since this part is less than 40, if I ask you what is the probability of the batsman scoring greater than 40, it's not very difficult. So 100% minus 2.23, and that is 97.77%. All right, I hope this is clear. So now let's move to the next problem. So let's look at problem number 2. So let's read the problem. You're a businessman doing grocery business. The supply of your stock is sporadic at times. Maybe you are not getting the supply from the vendors or the suppliers which supplies goods to your grocery store. You do not receive it very regularly. It's sporadic. At times you receive it on time. At times you do not receive things on time. So you even suffer losses at times if the goods are not sold within a certain period. Probably they cross expiry periods, which is very regular, especially with dairy products, right? Milk and all those stuff. If they are not sold within a certain period, you cannot sell it again because that's harmful. So you suffer losses at times and you make profits also. So profits have a mean of 2000 and a standard deviation of 1000, which very clearly shows that the business is very topsy-turvy. Though you make profits, but at times you do make losses, because the standard deviation, if you look at it, it's 1000, quite high. So your team makes 100 trades per week. So you do 100 transactions. Actually, transactions will probably be the right word. So your team who is running your shop, they makes 100 transactions per week. Now, what is the probability of your team, or rather your shop in this case, because your team cannot make profit, making a loss or making a profit of more than 20,000 in a given week? So let's dissect the problem. Let's first look at what we have. So we have a population data, which is the mean of 2000 and the standard deviation of 1000. So let's write down mean of 2000 and standard deviation of 1000, right, for each transaction. So your team makes 100 transactions per week. Okay. Now the probability, what we need to find out, the probability that you make a loss and the probability that you make a profit greater than 20,000. So here, when we look at a profit of 20,000 in a given week, considering that we are making 100 trades, you can actually say that per trade, if you want to look at, it should be because this is for the entire week across all the trades. We want to find out per trade, because mean and standard deviation, all of them signifies per trade. So we want to find out the probability of making a profit greater than 200. Actually, let's make the problem a bit complicated. Let's make this, say, let's make this, actually this is fine. Let's go with this. This is okay. Or let me just change these numbers a bit, maybe. So let me make this, say, profit of greater than 50,000, for example. Or rather, let's make it 5 lakhs, so that it becomes more interesting. 1, 2, 3, 4, 5. Yeah. So 5 lakhs, or rather, let me make it 3 lakhs actually. So here now we are looking at a profit of greater than 3,000 and a loss. Loss is less than 0. So let's draw the normal distribution. So this is my mean, 2000. This is my standard deviation, which is 1K per 1000, just to avoid a bit of space. 2 standard deviation will be 0. and in this side I'll just call it 3k just to save space. So now what do we need to find? Let's look at the problem. Probability of you making a loss, which means this particular region, and probability of you making a profit greater than 3000, which means the region, actually let me draw profit with a good color. It's profit, so let's use green. So we want to find out the probability of a random sample being picked up from the green zone and the red zone. Eventually that's what we are trying to find, right? If I pick a random sample, what is the probability that it will be from this green zone and it will be from this red zone? Now again, as I said, first visualize the problem intuitively. That makes life very easy. So it's intuitively very clear that the chances of you making a loss is less and the chances of you making a profit greater than 3000 is not very high, but at least it's more than you making a loss. So let's quickly crunch the numbers. So for the first problem, let's find out z is equal to 0 and we want to find this region. So loss means less than 0. That's what we wanted to find, a loss and a profit of 30,000, right? So loss is 0 minus the mean is 2000 divided by standard deviation 100, which is minus 2, and a z score of 3000 is 3000 minus 2000 divided by, it should be 1000. So now from the z score, let's figure out the p-values. So just to make the problem interesting, I will make a bit small changes here. I will say suppose this is 3200, say this is 3176. So this is the reason is I just want to show you how to look at certain decimal places in z score. So this will be 1.76. All right. So here we are looking at not this region, not greater than 3000 fully. Probably I'm looking at this region. This is 3176. And this is the shaded region. So now let's come here. -2. Same 0.228. So the p-value is 228, which means less than 0 is 2.23%. Now this one is 1.76. So let's come down to the positive side. So this is 1.7 and 1.76 is this one. So 1.7 and 0.6. This is 1.7. This is 0.6. So this is the p-value when the z-score is 1.76, which means this particular region is 0.9608, which we found from here. However, we need this region because we are looking at greater than 3176. So this region is 0.9608. So this region is 0.0392. So this part is 3.92% because I'm looking greater than z, and less than z is 96.08%. So let's go down. So here the p-value is, because I'm looking at this side, and the value which we get from the z table is always on the left hand side. So the p-value in this case is 1 minus 0.9608, as we are looking for greater than this 3176. Here is my 3176, right? The z-score the p-value which we get is always on the left side, but I did on the right side. I did more than greater than 3176. So in this case, this is 0.0392. So this one is 3.92%. Now from this, if you want to further derive that, if I ask you what are the chances that the shop will make profit, which means I am looking at this, and from here this should be 100 minus, let me use the same ink for calculation. So it's 100 minus 3.92%, which is 0.896. No, my bad. You should take this one, not 3.92. 100 minus 2.23. My apologies. So it should be 97.77. We are looking at this number. I hope this is clear now. So now we have solved two problems using z-score and p-value. Now let's take one step further and let's look at hypothesis testing. The steps are not going to be much different, only some small tweaks here and there. So let's start by looking at a problem of hypothesis testing. A quick recap. Before we start hypothesis testing, H0, H1. H0 is my null hypothesis, which is my anti-belief, which is something which I don't believe. H1 is my alternate hypothesis. Which is my belief, which is something more likely to happen. Right? Also, what we know is that we cannot test this directly. Because there are no statistical tests available to test the alternate hypothesis. So this can't be tested directly. So we test this, we test null hypothesis. When we test null hypothesis, we get a p-value. And what we want this p-value to be low. How much low? Ideally less than 5%. If that is the case, then we reject H0 and accept H1. So this is the high level flow of hypothesis testing, which I have already explained in deep detail. This is just to warm you up and a quick recall. So now let's start looking at the problem. So in 2015, kids were watching 26.5 hours of TV with a standard deviation of 8 hours. So in 2015, you did a survey and you found that kids were watching 26.5 hours of TV with a standard deviation of 8 hours. Since nothing is mentioned about what kind of distribution does it follow, we will assume that we are talking about normal distribution. So today, you randomly surveyed 70 kids and you found that they are watching 24.5 hours of TV. So in 2020, you randomly surveyed 70 kids. By the way, here the word randomly surveyed is very, very important. While doing any survey, it's very important that you do it randomly. Okay? Else you can just ask your kid, their friends. That doesn't work. You have to randomly pick up 70 kids and then you have to do the survey. And you found that they are watching 24.5 hours of TV. So now the question comes is, are the kids watching less TV these days? So in 2015, they were watching 26.5 hours of TV. Probably we are talking per week average. So today in 2020, which means after 5 years, you randomly surveyed 70 kids and found that they are watching 24.5 hours, which is less than 26.5. So the question is, are the kids watching less TV these days? So here, let's break down the problem one by one. So what is the information we have? This is problem number 3. So in 2015, kids were watching 26.5 hours of TV. And standard deviation is 8 hours. So we assume that this is my population. Since we have not mentioned anything, always assume that this is my population. Now in 2020, you randomly surveyed 70 kids and you found that they are watching, these 70 kids are watching around 24.5 hours. Now mind it, you have only surveyed 70 kids. Is that enough for you to say that the kids are watching less than 26.5 hours of TV? So in this case, what we want to find out is the probability of the kids watching 26.5 hours of TV, right? Given this arrow, this vertical bar represents given, means what is when I am looking at another condition, which in this case is n is equal to 70 and x is equal to 24.5. So what do we want to find out? The probability of x being less than 26.5 when I found that n is equal to 70 and x is equal to 24.5. N is the number of kids I surveyed and x is how much TV they want. So this part I know that this is true because I have done it. I want to find out if this is true, what are the chances that this is true. We want to find. Okay. So we want to find the chances of this part being true given this particular condition. So let's go step by step. Let's first write down what is our belief. It's from the initial indications, our belief is that kids are watching less TV, less than 26.5, because this was my benchmark. So if you look at the problem, we are saying, are the kids watching less TV compared to this 26.5, because this was my initial population. Here I have not mentioned what are the number of kids we have surveyed, so always assume that this is the population. And any hypothesis is always done on the population, not on the sample. Like what we do is, if you think of a real life scenario, we say that the average literacy rate of, say, India is 75%, for example, right? Now suppose you randomly surveyed 100 people and you found that out of those 100 people, 90 are literate, which means the literacy rate is 90% for those 100 people, right? So you get an intuition that probably the literacy rate has increased. But is it enough? Because you have only spoken to 100 people. You have not spoken to a lot of people. But is it enough for you to make an assumption that probably it is greater than 77%, right? So in this case, you have to think like this. You have to think intuitively first. Is it enough for you, by surveying 70 kids, that the population data, which in this case is 26.5 hours, has dropped? So what is my belief? What is more likely to happen? There is my alternate hypothesis. What is least likely to happen? Now you may ask me why this is not greater. Why it is not greater or equal to 26.5? The reason behind very simple is, it's very evident that the numbers have dropped. And it's very unlikely that this will be greater than 26.5. At best, it can stay at its current position, because we can clearly see that there is a drop here. But is that drop substantial enough? Or have we spoken to enough people to make a conclusion about the population of 2020, right? That's what we want to find out. So always think that in this case, the two questions which are important is that drop enough? Is the drop enough for me to conclude that it has actually dropped? Dropped enough means this and 24.5, right? Is it an enough drop? The second is, have we surveyed enough people? Right? So now let's try to solve the problem. So according to central limit theorem, what do we know? We know that mu equals to mu bar. This mu bar is the sample side. This mu is from the population side, right? So this mu bar belongs to the sample side. This I'll call the sample side. This is the population side. So according to central limit theorem, mu is equal to mu bar, which means in this case the mu bar is 26.5. The standard deviation of the sampling distribution, sigma x bar, is equal to sigma by square root of n. So sigma, as you can see, it's 8. 8 by n is 70. And that comes out to be 8.36. So 8 divided by 8.36 is 0.95. So the standard deviation is 0.95. So now let's draw this graph and let's try to mimic this condition here. Remember, this is not, I do not know whether this is true or not. I'm just trying to mimic it and see the chances of this statement being true. So this is my, according to this scenario, this is 26.5. So that's my mu bar. And my sigma x bar is 0.95. So So 26.5 minus 0.95 is 25.55, one standard deviation to the left. So this is 25.55 minus 0.95 is 24.6, which means this is two standard deviation away. And our candidate is 24.5, which is here. This part is 24.5. So now we have mimicked this in the graph. Now we have to understand one concept of rejection region. What is a rejection region? In very simple terms, rejection region is the region which does not contain 24.5 and 26.5, which means in this case this is my rejection region, the region shaded in blue, because this part does not contain 24.5 and 26.5. This region, the region on the green, that has both 26.5 and 24.5, right? This region. However, the region shaded on the blue does not have 24.5 and 26.5. So this portion is called the rejection region. Now logically, if you think, the closer this 24.5 and 26.5 come, right? That will increase the rejection region, isn't it? Like for example, suppose this is 10, is a number 10, there's a number 8, there's a number 6. So if we want to compare 8 and 10, the rejection region is higher. This is the rejection region of 8 and 10, right? Why the rejection region is higher? Because 8 and 10 are closer. The closer these 2 points are, the rejection region becomes higher, right? So in this case, it's very evident that these 2 points are not very close, which was also which is something which we also saw. This is 26.5 and this is 24.5, right? So they are not very close. What we want to find out is the coexistence of these 2 things. We do not know whether it's less than 26.5 or not. That's what we want to find out. When this part is true, this part is what we want to find. What is the probability, right? So the probability of this thing happening, this particular phenomenon, this particular probability happening should ideally be low, right? Should ideally be low if the rejection region is less. The rejection region, if it grows higher, then we get a higher chance of these 2 statements being true at the same time, isn't it? So logically think, in this case, the chances of 8 and 10, since they are closer to each other, the rejection region is higher, which means, for example, if I say that, what are the chances, what are the probability of mu being 10 if I pick up a random sample which is 8, right? And the chances of mu being 10, suppose if I pick a random sample which is 6. In this case, this chance is higher because these 2 points are closer. And a closer point means a higher rejection region. The lower rejection region indicates that probably the chances will be very, very low. How much low? Let's figure out. So z-score of 24.5, you already know, it will be 24.5 minus 26.5 divided by the standard deviation 0.95, and that is minus 2 divided by 0.95 is minus 2.10. So the z-score is minus 2.10. So from the z-score, I will get the p-value. I want to get the p-value of this region, and we know how to get that. So minus 2.1 is, sorry, this is the positive side. Minus 2.1 is 0.179, which means the probability of us, or the rejection region probability is 0.179, which is 1.79%. So the p-value here is 0.179, and this p-value what we get is for the rejection region, right? So now the formula is very simple from here. The p-value which we calculate, if it is less than rejection region, we can say that reject H0, right? In this case, what is my H0? My H0 is this. That is very, actually, you know what? This is not correct. This should be the ideal formulation. That it is 26.5, the total, actually even this is not correct. Yes. So the probability that the mean is 26.5 given that this particular thing is true, right? So the probability that this is 26.5, which means the probability of these two statements coexisting, co-occurring, and this can only be high if the rejection region is high. When the rejection region can be high? If these 2 points are closer. If these 2 points are closer, what will happen? The z-score will be lower, right? So think about this sequence one by one. So p-value is less than rejection region. I reject H0. Why? When the p-value can be less than rejection region? When the p-value can be less, actually you should know, it should not say like this. And this rejection region ideally should be 0.05. Now it's complete. So the p-value, what we calculate, if it's less than the rejection region where which should be 0.05, then we reject H0. When the p-value can be less, if the z-score is high, isn't it? When the z-score is high, if chances of two statements coexisting is high. Now what do I mean by that? Like in this case, we are looking at the coexistence of the statement that the mean of the distribution is 10, but we picked up a random sample which is 8. There are a lot of numbers. I pick up a random number, there is 8, and I know that in this case my mean is, say, so I'm looking at a distribution where mean is 10 and standard deviation is, say, 2. So I pick up a random sample which is 8, where I got 8, right? What are the chances that the probability, or what are the chances that the mean is 10? So the mean is 10 and I pick a random sample that is 8. Now this one I know is true because I have done it. What are the chances if I pick a random sample which is 8 and the probability is 10? Sorry, the mean is 10. The probability of the mean being 10 when I have picked up a random sample which is 8. That's what we want to find out. So if the z-score is, high, then this happens. If the z-score is low, then the chances, the probability of coexistence, two statements coexisting, will be low. Right? So if the z-score is low, means 2 points are far apart, the p-value will also be low because the rejection region will be low. So lower, if the 2 points are far apart, the z-score will be high, the p-value will be low, the rejection region will be low, and we can reject the null hypothesis. Right? So in this case, what p-value did we get? 0.179. So this is what we have got. That is less than 0.05. So we can reject the null hypothesis. My null hypothesis is this, which is rejected, means the chances of this statement being true is only 1.79%. Right? This one multiplied by 100 is 1.79. So this one has a chance of, this has only 1.79% chances, means this one has a chance of 98.21%, and we accept the alternate hypothesis, or rather we can say that we are 98.21% sure that people are watching less TV, but this number is so high, you can actually pass it as a judgment. We can say that people are watching less TV. I hope the entire understanding of the problem is clear, because now we are going to just extend the same thing for other problems. So let me share a small tip with you. So far we have been trying to calculate the p-values, and going forward also we'll keep on doing that because that's a good practice. But let me also show you a shortcut. Do we really need to take the z-score every time? Sorry, do we really need to take the p-value from the z-score every time? I'll tell you a shortcut so that I don't even need to look at the p-value. And just by the z-score, I should be able to make a conclusion. So what is that concept? So what I want the p-value to be less than 0.05. How do I get the p-value from the z-score? Right? So now what we'll do is we'll learn a shortcut. So in order for the p-value to be less than 0.05, let's find out what is that z-score. So let's come to the z table. So let's look at a negative z table where the value, where can I find a good p-value where it is just less than 0.05. This part, this is my cutoff, so which is like minus 1.65, as you can see. This is just below 5%. So let's write down minus 1.65, and from the other side I will try to find out where exactly it is just crossing 95%. And if we see this, again 1.65, which means the rule is if the z-score lies between minus 1.65 to 1.65, you cannot reject a null hypothesis. If it's beyond this range, then you can. So if the z-score is greater than 1.65, or if the z-score is less than minus 1.65, if these two scenarios occur, then you can reject null hypothesis considering that my confidence interval is 0.05. If this is 0.05, which is generally the norm. The general norm is that the confidence interval is 0.05. If that is the case, if this is the scenario, then a z-score greater than 1.65 or a z-score less than 1.65, I can reject the null hypothesis. Okay. Now suppose, for example, if your z-score is, suppose I say, okay, now I want to have a confidence interval of say 0.09, which means suppose it's a very mission critical, so I want a confidence interval of 0.01, which means I want to be 99% sure of my alternate hypothesis. So in this case, the p-value has to be less than 0.01. So in that case, what we'll do is, let's look at the positive side, which means I have to find where it is just greater than 99, which is this point, 2.33. 2.33. So in this case, a z-score greater than 2.33 or a z-score less than minus 2.33. If either of these scenario occurs, then you can reject H0. Else we fail to reject H0. So this is a small tip which you can use. We will continue to use p-value because that gives a more intuitive understanding. But this is also a shortcut which you can follow to quickly do your calculation. Okay, so now let's look at the next problem. So if you can see, let's solve problem number 3. So average IQ of all kids, and here when I say kids, I mean all kids of the country, say is 110 with a standard deviation of 5. Fair enough. So we visited a particular school whom we are calling school A, and we randomly surveyed 50 kids within that school and found out that their IQ is 120. So what we can infer about school A kids? So what we see is that the national average is 110 with a standard deviation of 5. However, when we visited a particular school and randomly surveyed, by the way, we have to emphasize on the word randomly surveyed. We cannot survey our known people and say, okay, I'm done. We randomly picked up 50 kids and we found out that their IQ is 120. So my first impression is that probably school A kids are having a higher IQ. That's my intuition. But is it true? We'll find out. I have surveyed 50 kids. Is it enough? We'll find out. Initial impression looks like it is high. But is it really high? Let's find it out. So let's write down the problem. So for population, we have a mu or a national average of 110. Sigma is 5. As far as sample is concerned, we know that n is equal to 50 and x is equal to 120, right? Now if I apply central limit theorem, so mu is equal to mu bar is equal to 110 and sigma x bar is equal to sigma by square root of n. So sigma is 5 divided by square root of 50. So we'll first find the square root of 50, which is 7.07. So 5 divided by 7.07, and that is 0.7. Okay. Now what is that we want to find out? We want to find out the probability that even before finding out the probability, let's write down the important step. That is the alternate hypothesis and null hypothesis. So alternate hypothesis is that mu equals to, or rather mu is greater than 110, and alternate hypothesis is mu is equal to 110. Now I have said before, there is no point in doing less than, right? At best it can be equal. It's very unlikely that it will be less than, for these kids it will be less than 110, right? So now what we are trying to find out, we are trying to find out the probability that the average IQ of school A kids is 110, given for randomly surveyed 50 people it is 120. This is what we want to find out. And this is nothing but the probability of my null hypothesis. So now let's draw a normal distribution. So if we assume that this is 110, so 110 with the standard deviation of 0.7. So 0.7 is 110.7, then 112, right? And somewhere here it will be 120. Let me draw it a bit nicely. Right? So this is 110, this is 120, and this is my rejection region. The region which does not contain 110 and 120. Always that is my rejection region, remember it. So let's find out the z-score of 120. So z-score of 120 is 120 by minus 110 divided by 0.7, and that turns out to be 10 divided by 0.7, and this number is a very, very large number. Very, very large. Which means we'll get a p-value which is very, very low. Which means that we can perfectly reject this and we can accept this. Okay. Now if you intuitively also see, if the new average, right, the new average should be actually not 110 but maybe 115 or maybe something else, but it cannot be 110. These 2 points are like so far ahead, away from each other, and the z-score is so large. As you can see here, the z-score will be like 10, 11, 11, 12, 12, maybe 13, 14. Z-score will be like 14, which is a very, very low p-value. So we can comfortably reject this null hypothesis and accept this alternate hypothesis, that there is hardly any chance that the IQ, the average IQ of the kids in the school is less than or actually equal to 110. It has to be greater than that. Let's tweak some parameters and see if we can make any difference. Suppose let's increase the standard deviation. Say the standard deviation, let's make it 20. Let's see now if it makes any difference. So in that case, this becomes 20. So 50 square root is 7.07. So 20 divided by 7.07 is 2.82. So this is does that make any difference? From the naked eye, it doesn't look like. So if this becomes 2.82, still it's not, it's like the z-score is still very high. So 10 divided by 2.82 will be close to 3 point something. 2.82 is 3.54, still very high. Doesn't make much of a difference. Okay, now let's make some changes. Say this is not 120, say this is 115, or say 112. Now let's see if that makes any difference. Actually, let's make it 115. So in that case, this is 115. So this is 5 by 2.82. So 5 divided by 2.82 is 1.77. So this value now becomes 1.77. Now if this becomes 1.77, then let's try to figure out p-value from the z table. So this is the z table. So 1.77. So 1.77 will be, no, this one. So this is so 96.16. So this side is 96.16 and this side is 1 minus 0.9616, which equals to 84, which means here the p-value is slightly better, slightly respectable. We were getting absolutely no p-values at all. Very low p-values we are getting. So this is 3.84%. Still lower enough for me to reject the hypothesis. I hope this makes sense. Now let's look at the next problem. So the problem says, in a survey conducted 2 years back, we found that 60% of household had got tablets. Today, you surveyed 200 random households and found that 68% use tablets. So what we can infer? Interesting. So today we can see on surveying 200 random households, we found that 68% is using tablets, which is higher than a survey conducted 2 years back. So we can clearly see that it's higher. But is it enough that we can say that today people are using more tablets? Let's figure out. So let's first write down the population information we have. The population information is 2 years back, 60%, right? 60%. And the standard deviation is, oh, we don't have any standard deviation. Also, the problem looks a bit new. So far, we have been dealing with whole numbers. Now we have suddenly got percentage. Neither we have any standard deviation. So we have to do something about this. First, let's convert it into decimal. And in this case, the standard deviation is 0.6 multiplied by 1 minus 0.6. So square root of mu, so the formula is mu into 1 minus mu. So which is 0.6 into 0.4. Square root is 0.48. This is my sigma. Now when we talk about sample, we have surveyed how many people? 200 households, and we found 68% are using tablet. So this is 200, and we found that 68% are using tablets. Okay. Now, according to CLT, Central Limit Theorem, mu equals mu bar equals 0.6, and sigma x bar is equal to sigma by square root of 200. Actually, let's try to make the problem a bit interesting. Suppose this is not 6.8, say this is 6.3. That will make the problem a bit interesting. So 0.48, first let's take square root of 200, 14.14. So 0.48 divided by 14.14 is 0.03. Okay. So according to Central Limit Theorem, we find this as 0.03. Now let's look at the null and the alternate hypothesis. So my alternate hypothesis is that mu is greater than 0.6. Very evident. Here this is 0.6. 0.63, and null is 0.6. Now what do I want to find? The probability of mu is equal to 0.6 given n equals to 200, x equals to 0.63. So now let's find out the z-score. So z-score of 0.63 is 0.63 minus 0.6 divided by 0.03. 0.63 minus 0.6 divided by 0.03, which is 1. So the z-score is 1. So now if this is 0.6, this is 0.63, and this side is my rejection region. So let's find out the z-score. 1 is 0.8413, which is this side. My rejection region is this side. So I have to do this. 1 minus 0.8413, and that is equal to 8715, which means my p-value is 0.1587, which means this one is 15.87% p-value into 100, just to take it in terms of percentage, which means, sorry boss, I can't reject I do not have enough evidence to reject the null hypothesis. I cannot accept alternate hypothesis. I do not have enough evidence to reject the null hypothesis. I cannot say that mu is not equal to 0.6, or I cannot say that mu is greater than 0.6. So that's it for today. We'll continue with few more variations of this problem. I hope you are liking this series. If you like these videos, please subscribe, comment, share. And if you want to enroll for the course, please click on the link below. Till then, happy learning.